yeah, let's now take a look at how we train a logistic regression model. By that I really mean like computing the gradients of the loss function with respect to the weight and bias parameters in the logistic regression model, so that we can then use gradient descent to update the model. And then in a later video, we will see how we implement that in code to do the actual practical training. So yeah, let's take a look at the logistic sigmoid function again. So here on the left-hand side, that's the logistic sigmoid activation function that we talked about before, where we have the net input on the x-axis and the output on the y-axis. It has this sigmoidal shape. And you can already see, just by looking at this function, what the gradients might be. So you can see here the function on the ends, it's relatively flat, so the gradient should be also very flat, like 0 around that region. And the steepest part is here, so this should also be where the gradient is the largest, or let's say the partial derivative with respect to the input is the largest. Now, on the right hand side, I was computing the derivative of the sigmoid function with respect to its input. So if you use the simple calculus rules, so that's how you would compute the derivative of this part, right? Because you have the derivative of the numerator, which is e to the power of minus z, the one cancels, and then you have this square term in the denominator. And when you solve that, I'm not doing it here, so when you solve that, if you're interested, I've done that in the Python machine learning book. I think it's in chapter 12 somewhere, but I can also share that if you're really curious about that. But you can probably also find examples of on the internet. It's quite involved. It will take you a few sheets of paper, I guess. But what the result is this one here. On the right-hand side, that's the derivative of the logistic sigmoid function. And you can see it's relatively simple, right? It's just the sigmoid function times 1 minus the sigmoid function, right? So that's what I mean, it has nice derivatives. There's actually one little, not so nice part about this activation function or its derivative. We will talk about that in a future lecture. So what's not so nice about it is actually that, these parts here of the derivative are actually 0. So here we don't have any, power to update the function. So if these terms are 0, this might be a problem when we have multi-layer neural networks and then have a chain rule where part of the chain rule is 0, because then the whole loss gradient becomes 0. But this is something we will talk about later. So let's now just focus on how this function looks like. So in the right lower side here, I have the derivative of this logistic sigmoid function. And you can see, like as with our intuition here, this part where z is 0, that's where the gradient is the highest, or the partial derivative is the highest. You can see the partial derivative is 0.25, the largest value. And then for very negative and very positive inputs, the derivative goes down to 0. It's you can see that here where it's also very flat, right? So this is how the logistic sigmoid derivative looks like. So and here is how the loss function looks like. So at the bottom here, this is again my negative log likelihood loss I talked about in the previous video. And like we talked about before, there are two parts really of this loss function. You can really think of it as the part when the class label is 1 and the part when the class label is 0. So here we really talk about the true label in the dataset, the label of the training example. And this is also the true label. So these are the true labels provided in the training dataset. Again, we only compute, this might sound trivial, but just to recap it, we only compute the loss function during training, not during prediction, right? When we have a test set or something and do a prediction, we don't use the loss. It's really just to find the weight parameters of the model. So we are given these true labels from the training set. So what happens if the true label is 1? Let's consider this scenario. If the true label is 1, we have a 1 here, right, on the bottom, and we have a 1 here. And here, if we have a 1 here on the right-hand side, then this whole term here becomes 0, and then we have 0 times something, so this whole term cancels. So if the true label is 1, we really only focus on this part here. if the true label is 1, then our loss function is minus log, and I can just write this part as A, the activation. It's minus log of the activation. Now, if my label is 0, then let me erase this. This is maybe a little bit messy here. So we set minus log of A, and for this right-hand part, if y is 0, then this part will be 0. 0 times something cancels. Here we have a 0, so this will be 1. So if the true label is 0, then the loss function is minus log 1 minus A. Now let's take a look at the shape of these curves here. So if we, let me use, I should have maybe used yellow, minus log 1 minus A. So it matches this orange or yellow line here. So you can see for the value here of the sigmoid function. So this is really like the logistic sigmoid, the class membership probability. And recall this one is for, use maybe the black color. This is for the class label equals 1. So the class membership probability for 1, class 1. So this is really like this probability here. So if what we want is this probability to be high if the true label is 1, and we want this probability to be low if the probability is 0. So, but we can also write this as 1 minus y equals 0. This is if it's easier to think about. So let's take a look at now what happens if this probability here is high. So if this whole term is high, this means if we have a low probability that this is indeed class 0. So if we have a term here, if we have a low probability for this one will have the whole term with a 1 minus included will have a large probability, and you can see we have a high loss in this case. So if we have a probability for class 1, so this is really like the class 1 probability. If this is high at 1, then we have a very large loss. You can see that. So the loss approaches infinity if we have a high probability. Vice versa, the loss approaches 0 if we have a low probability here, right? So you can see that the closer I get to a low probability, that the class label is 1, the smaller the loss. Because a low probability for class 1 means a high probability for class 0, which is what we want. So here, if the true label is indeed 0, we want a low probability for class 1. So here we have a 0 loss if we have a 0 probability for class 1, because then the probability for y equals 0 will be large because of this relationship here. The same way, now let's take a look at, let's use the blue color, the case when the class label is 1. The same way, when we have a low probability for class membership 1, we have a high loss, it approaches infinity, right? Because, we will never really have a probability of 0. We will hopefully have something like very, very small, because otherwise it will crash our log function. Or, yeah, so we will have minus log of 0, right? So it will be a very small number. And then this approaches, this loss approaches infinity, basically, if we have a low probability. And we have a high loss, if we have a high probability, the loss will be very low. That's what I wanted to say. So the takeaway here is really, this is how our loss function looks like. What we want is, we want to have a high probability for the right class, and a wrong probability, like a low probability for the right class, or a high probability for the wrong class, consequently, will result in a very large loss. And you can see it's like steeply increasing here. So that's the takeaway. So there's a large penalty for making a wrong prediction. yeah, how does the learning rule now look like? I mean, this is the same gradient descent rule that we used before when we trained a linear regression model or add a line using gradient descent. For that one, what we needed was the derivative of the loss function with respect to the weights. So that's the partial derivative of the loss function with respect to the weight. And we also compute the partial derivative of the loss function with respect to the bias. That's the same concept. So in order to do that, we can compose it into 3 terms. That's the same as we have done for Adeline and linear regression. So we compute the derivative of the loss with respect to the output of the activation function. Then we compute the derivative of the activation function with respect to the input. For Adeline, this was just 1 because the activation function was identity function. And then what we also compute is the derivative of the net input with respect to the weight. And that was just x, right? xj, similar to Adeline. So here at the bottom, I've written this out. So all these 3 terms. So this one, by the way, this is the negative log likelihood hood loss that we talked about in the previous slide. And if you look at this, the only thing that's really different from Adeline is that these and these values are of course different because we have a different loss function. In Adeline, we had the MSE, right, where the derivative, so the MSE was, for example, written like this. Let's say like this with the 1/2 in front. And we can also do the 1/n if you like. But, okay, so let's do it. And then we bring the 2 up front for the derivative. So it's 2/2n, so the 2 cancels. So we just have 1/n times, just minus, sorry, it should be y hat minus y. So that would be the derivative of our MSE. Now, of course, we don't have an MSE. We have this negative log likelihood for which we have the following derivative with respect to the activation function, with respect to its input. And this one for Adeline was 1. And this one is the same because the net input is the same. Now, the only thing we have to do really is to put those together, right? We have to just multiply them using the chain rule. So it's the same like for Adeline. For Adeline, it just looked simpler. But for Adeline, we just had 1/n times y hat minus y times xj, right? So that was the one for Adeline. For the logistic one, it may look more complicated because we have now this term and this term. However, there's something nice that's happening. So we can actually, I'm not sure what I've done here, we can actually simplify this. So this part and this part, when we put them together, it simplifies to this one here. So you can work out the math if you like, but it's a simple, very simple derivative here. So you can see that these cancel each other nicely. And this is why I said that the logistic regression or the sigmoid function has nice derivatives. That's because things cancel here nicely. And then we just add the x to it. And you can see, actually, this looks exactly like the Adeline learning rule, right? This looks exactly like the linear regression one, right? Isn't that quite cool? So here is just from the previous slides that we had on Adeline and linear regression. So this was the stochastic gradient descent learning rule here, where we had the initial weights, the for loop over the training epochs, and then the for loop over the training examples. That could also be for mini batches. Then we compute the prediction, the gradients here, and then we do the update here. And then we had the learning rate eta here. We can use exactly the same rule for logistic regression. Also note there was also a discussion on Piazza. We can actually rewrite this, because I think I've done it the other way around in code. We can actually rewrite this as, of course, like y hat minus y, right? It's the same thing because we have minus and minus. And that is what I had in the previous slide. If I go back, I have a minus y instead of y minus a. So I should say that a is equal to y hat here. So that's the output of the logistic regression model. So a and y hat are the same thing here. So let me write just A here. So what I mean, we can also write this, maybe it's, if it's more clear, oh, I can't erase more. Let's maybe write this as A minus Y xj, and this one should be just A minus Y. Oops, yeah. So this is exactly the same learning rule as for Adeline. What's the difference now? Why is this a logistic regression? Well, the big difference here is that A is computed differently, right? So A is now computed via this nonlinear function, whereas for linear regression, it was, or Adeline, it was just computed as the identity function. So in the case of Adeline or linear regression, this was the net input. So, but yeah, that is again why I said it has nice derivatives, because we don't even have to change our learning rule. The only thing we have to change is how y hat, or basically A, is computed. All right, so a few last things about this. So here we can think of this as the whole computation graph again. This is our logistic regression computation graph. We haven't talked about this output yet, right? So we do the training here. So here's where we compute the error. So we have a true, let's say, a true label. Let's call that true label y. That goes in here. And here, what comes out is our A, or y hat. Let's call it y hat. It's actually a probability, so it's maybe more clear to call it A. So we have our A and our true y, and from that one we compute the negative log likelihood, compute the gradients or the partial derivative of the loss with respect to each weight, and also the bias. So here I'm actually not showing the bias, I just see. So it should be technically also a bias unit. So we compute that one, and then we update the weights and the bias units with that one. And this right part here, this comes after training. This is just for the prediction. So for that one, we can use a threshold function similar to Adeline. So in logistic regression, we can use the following threshold function here to compute the real y hat. So I should have maybe be more consistent and say y hat is the predicted class label and A is the probability, class membership probability. I will be more careful of that when I write the code for the next video. Anyways, so we can say with this threshold function, if the probability, so this is A, if this is greater than 0.5, then return class label 1, and otherwise return class label 0. Actually, we can do it even more computationally efficient during prediction. We can even skip the activation function, and we can just operate with Z. We can say if the net input is greater than if it's greater than 0, then the label is 1, otherwise it's 0. Why is that? If we take a look at the logistic sigmoid function again, so here that's the net input at 0. So at 0, the output is 0.5. So we know, so we can say everything above here, above 0.5, is class label 1, say y hat class label 1, and below here y hat is class 0. But we know if we have the threshold 0.5, it corresponds to a net input of 0. So we can also just say if the net input is greater than 0, then it's class label 1. If it's smaller than 0, then it's class label 0. So that's just what I wanted to say about logistic regression. In the next video, I want to talk a little bit about the logits and cross entropy. These are just two, I would say, jargon words about or regarding logistic regression, logits and cross entropy. I will just briefly discuss what those mean, and then I will show you logistic regression in a code example. And if everything in this video was a little bit fast and confusing, I think the code example will probably clarify that, because then we will put everything together. We will do the forward pass, compute the gradients, and update the weights. So what I mean is we will really implement this whole stochastic gradient descent learning rule in code, and that I hope clarifies everything.